Hello everyone, thank you for attending my presentation. Today I will be talking about my course project in image processing and computer vision. My topic name is called Sensor-Assisted Image Registration and Tracking for Augmented Reality Application. My name is Kakaru. So first let's talk about what's the augmented reality applications. Augmented reality is a kind of mobile application and it can actually let you see more of your surroundings. Just like let the right figure show that when you open your smartphone camera, and you can see more from your camera views. For example, you can show the name tags or building names or the physical buildings or the Wikipedia's around you or other related information. Even you can leave you can see some notes lived in your space. It really actually bridge your physical world to your virtual world and bring your physical world more virtual information. The basic problem is that in augmented reality, you need to maintain and track the overlay information, and when the camera moves and detect this point of interest, when you move your camera and provide more information to the users. Like this figure shows the name tag shows new engineering buildings, and it's really attached to the real physical buildings. And when you move it really sticks to the physical building, and so it can let you know more of your surrounding. So the main task of this project is to we need to how to present an augmented view in a smartphone. We need to know the intrinsic and the extrinsic matrix and know the exact locations of the point of interest in your camera views. And you also need to predict which POI is in your camera view. Besides that, you also need to examine and check the current sensor image to the POI image database using image feature detection and matching. It is different from purely image matching based augmented reality because we actually predict the POI in your camera view through the inertial sensors. So you actually only need to perform the image matching for the detected POI. Then when your camera moves, we need to track the AR view. So this is 4 basic tasks in our project. This is our proposed system architecture. First, we get the image and the sensor data and perform per processes. Then the sensor data will be used to calculate the displacement of your smartphone and your attitude. Actually, the basic model of the smartphone camera is kind of rigid motion models. So every model can be divided into the rotation and the translations. So we can use the inertial sensor in the smartphone to get the location and the attitude of the smartphones, and using this information to assist the image matching process in your smartphone. For the image processing, we actually perform the feature extractions from the image, then perform the matching and from with the images from the cloud database. Then when we have image registration, and then we can present the augmented reality overlays. Before we talking about the system details, we first talking about the system models. The first model we want to talk about is the body coordinate. We define the body coordinate as actually the center is in the smartphone. So when we move our smartphones or cameras, the body coordinate also changes. So the body coordinate is actually attached to your smartphone. So all your inertial sensors or the camera view is actually related to the body coordinate. Then through the camera view, so a physical target will be matched to the image view that is on user's smartphone screen and rendered by the pixels. Another coordinate is called navigation coordinate. Navigation coordinate is actually the local absolute coordinate that you can actually navigate navigate, like a map of the indoor building or the map of your campus. The navigation coordinate is actually related to the the east-north up coordinate of the Earth. Navigation coordinate is actually the local version of the ENU coordinate. So when using your smartphone, you get your GPS location. So if your GPS location is the longitude and the latitude, you need to transform to the ECEF coordinate, that is Earth center, Earth fixed coordinate. Then from the ECEF coordinate, you can translate to the east-north up coordinate. So this is all the coordination system that we use in this project. First, let's deliver the intrinsic parameter. We call it the intrinsic parameter because it is really related to the camera itself. First, we define a sense point. The sense point means a real physical point in the body coordinate. We denote it as the xb. So the image point in the image plane, we name it x pi. So actually the projection matrix can be mapped from the sense point to the image point by using the matrix P. And then the image, then the point in the image plane actually to convert to the pixels in the screen. So we need another matrix. So to combine all the matrix together, we know that we can convert from the sense point xb to the pixel point in the screen by using the K matrix. So K is actually the intrinsic parameters of the camera. Since we need to utilize, we need to implement the systems using the smartphones. So we actually need to convert over intrinsic parameters within the OpenGL framework. So within OpenGL framework, we need to slightly change our the K matrix. We actually add one row to record the Z information. So from the final K matrix, we know that the far plane and near plane is the far plane and near plane. So we can calculate the new kg for the OpenGL system. Yeah, previously we talked about the intrinsic parameter. Then we talk about the extrinsic parameters. Actually, this parameter is related to the motions of the smartphone or the cameras. For example, we know that over the camera's rigid motions can be divided into the rotation and the translations. So we actually can map a point in the navigation coordinate into the body coordinate using this rotation matrix and the translation matrix. And the navigation, so combine all this intrinsic and extrinsic parameter together, we actually can directly convert a point in the navigation coordinate to the image pixels by the projective matrix P. So here we summarize the process to present the AR view in user's smartphone. So first we need to obtain the smartphone positions and then convert the smartphone position into the navigation coordinate. Then we need to utilize the inertial sensors to estimate the body attitude of the smartphone in terms of the rotation matrix and the translation matrix. So in real implementations, we achieve very high flash rate for this inertial data. Then we need to update the camera projection matrix. Then we actually need to predict which POI location is in your camera view. So we iterate all the local POI positions and compare their projected position on the screen. Then predict which POI is actually on your smartphone screen. Then we can actually perform the image matching for the predicted POIs to match with the POI's image database. If it actually matches, then we can retrieve the augmented information related to the POI. Then we can use the OpenGL to render in the overlay view for the detected POI. Then your smartphone move, you can actually track the POI when your smartphone moves. So you can use the image matching or use the inertial sensor and the detail of the process we will talk later. Yeah, after know how to present the AR view, we need to know the detail to how to estimate the motions. That is the motion. We know that almost all smartphones have the MEMS sensors. We can have the gyroscope accelerometers. So we can use the gyroscope to estimate the rotation matrix or the attitude, and using the accelerometer to estimate the displacement. Then we can calculate the Euler angles like the low PGR of the smartphone. So the gyroscope is actually measured the angle velocities. We name it the omega t in the body coordinate. Then perform the integration, we can get the rotation angle. Using these equations, we can get the Euler angle rate. Then perform the integration, we can get the Euler angles of the smartphone. Whereas the Euler angle is actually the attitude of the smartphone. And this figure shows our experimental result when we move over a smartphone. So we can see that when we keep it stationary, the low PGI actually also keep it stationary. So in these 4 moving regions, the low PGI actually changes. It is very accurate. Then we actually, for the accelerometers, the measurement is actually called the F and the TB. Then we can get the accelerations using the rotation matrix, the R, and minus the gravities, we can get the accelerations that is forced, that is attached, that is or forced into your smartphone coordinate. Then we can calculate the velocity in the navigation coordinate and calculate the displacement of your smartphone. Well, the displacement actually is the translation matrix. So here it shows the over motion estimation result. So when we move your smartphone forward and backward and again, so if there are some we can in this figure show that actually the start position and position is actually coincide with each other. So it shows really small drift. The most problem of the initial sensor is drift, but over accuracy it shows very good result. This figure also shows that the start position and the end position is only about 10 centimeters drift. It is very small. And this is the motion estimation result when our smartphone moving in rectangular. So the distance is about 1 meters plus 1 meters. It is really a large place for using the inertial sensors, and we can achieve very good result. The start position and the end position has very small drift, and the motion and the movement, the traces is very clear. After obtaining this rotation and translation matrix, then we can perform image matchings. First, we perform feature detection and matchings. Unlike the normal augmented reality approaches purely using the image matching, we actually can reduce image matching database. So we actually predict the POI in your camera view. So we can only perform image matching for your predicted POI. Then we actually utilize the SURF surface feature detection. Surface feature is actually the robust local feature detector. It is better than the conventional features like the point feature, line feature, and corner feature. And it can achieve multi-resolution accuracies using the wavelet transform. After using the correlation-based matchings, we achieve the image matching result. But there are also contains lots of outliers. So we're using the Rancic algorithms to remove the outlier. The Rancic is actually a very powerful iterative and non-deterministic method for to remove the outliers. The basic way for the recipe is actually assumes like the data consists the inlines and using the model to predict the inlines. So all the outliers do not fit the inline. So using this model, they actually can mitigate the outliers. And the left figure shows the overused the surf features in image detected features in image 1, and the right figure shows that the several strongest surf features in image 2, and they all show that some strongest surf features with the large diameter of the circles means the larger features. Then the left figure shows the image match result. The left figure is actually the putative match result. Means that it is just the correlation match result, and there contains lots of errors like this one. So after using the RANSEEK to remove the outliers, we can get a very clear result. So after the image matching process, we can actually utilize the motion assistance to the image matchings. We know that our camera rigid motion can be divided into the rotation and the translation. So we actually can utilize the epipolar geometry and estimate the fundamental matrix by using the intrinsic matrix of the camera, the translation matrix, and the rotation matrix, and show these equations. But sometimes your smartphone do not have the translation, you just to have some rotations. That is, the baseline in the epipolar geometry is 0. So in these cases, the fundamental matrix equation may not hold. So we actually utilize the homographic matrix. The homographic matrix only counts the rotations, that is H. Then we can utilize the H matrix to obtain the F-line image wrapping between the image 1 and image 2. So the last step is actually we perform the image rectification. The reason we perform the image rectification is to simplify the matching process, because the image matching is actually a local matching process. It has a converging regions. So if the two images are more similar to each other, so they may have a very high probability of the matching. So using our motion assisted approaches, we actually can estimate the image 1, estimate the projection of the image 1 to image 2. So although there contains some errors, the matching difference from the predicted image into the image 2 is actually smaller than the initial 2 images. So it can really actually improve the matching probability. So the left figure shows that after using the motion assisted image rectification, we know that the initial image and the image 1 and image 2 has small differences. So the translation between two images is really small. So they have very high probability. They get very more than 2 times the numbers of the matching numbers. Then after remove the outliers of the RANSEEK, the total obtained match numbers is more than 2 times or 3 times than the image. So the improvement is significant. So let's have a conclusion. So in this project, we talk about the augmented reality mobile applications, and we know that the augmented reality application is really excited, and we also talk about how to present the AR view in smartphone screen. We talk about the intrinsic metrics of the camera and the motions of the smartphone, like the estimated the rotation and the translation matrix of the smartphone using the inertial sensors. We also predict the POI in the camera view and perform image matching for the predicted POI. We also perform image rectification using the motion data before perform the image matchings. This will actually assist the matching, and we can get more matching result. That's all. Thank you.